Hello, everyone. Welcome to this week's Crunch seminar. Today we have one speaker. Our speaker is Dr. Peiyuan Gao, who is a research scientist in the Pacific Northwest National Lab. He earned his PhD in chemistry from the Institute of Chemistry at the Chinese Academy of Science, where his research focused on development of multi-scale modeling and simulation approaches and application in soft matter physics. After completing his doctoral studies, Dr. Gao transitioned into the role of a postdoc and then was promoted to a position of research scientist at PNNL. His current interests encompass multi-scale modeling and simulation of energy storage materials and scientific machine learning algorithm and application to molecular systems. Dr. Gao, thank you so much for joining us today. We're excited for your talk, and with this short introduction, you can start whenever you're ready.
Yeah, thank you for the brief introduction. I'm Peiyuan Gao, a research scientist from PNNL. Today, I will talk about some my recent work on multi-scale modeling with machine learning, mainly on the fluid systems. This is the outline for today's talk. So first, I will give a brief background on the multi-scale modeling and simulation with machine learning. I know usually we are interested in both simple and complex fluids, but today, mostly I will talk about the multi-scale modeling on simple fluids with machine learning. And the machine learning method, I will focus on neural networks. Then I will show you two frameworks and application with the framework. So the first one is to develop the chemically specific coarse-grained fluid model with both consistent structure and dynamic properties. The second one is application of physics-informed machine learning and deep net in the thermodynamic properties prediction of the bulk fluids. So first, let's show an overview for the multi-scale modeling from an applied science perspective. So for the real systems, usually we start with one atom, simulation of one atom. So the long scale would be from angstrom, maybe a couple of angstrom. And the time scale usually is 1 femtosecond. It is 10 to minus 50 seconds. But in practice, maybe sometimes we will also use even smaller time step, like 0.1 for specific problems. And for the initial modeling, actually, we will solve the Schrodinger equation to get the position of the both the atoms and the electrons. So you know the solution of the Schrodinger equation is not easy. So we usually we know it only works for three particles in the system. Then we will need some approximation, like the density functional theory, to expand the system. But they are still expensive. So usually for the initial modeling, the long scale is only several nanometers, and the time scale is only tens of picosecond. Then up to the other scale, we will use atomic modeling with some approximation and some parameters from initial modeling. The time scale could be tens or hundreds of nanometers for the current computational power. And the long scale could be several or hundreds of nanometers. But for even larger system, we will need to coarse grain them and build a mesoscale modeling model to simulate a larger system. And then if the long scale is close to it's several hundred micrometers, we can use the continuum level modeling, like the process modeling, and the time scale could be several seconds or hours or even day. And then for a large system, we can do some modeling at the system level. This is actually I will call it system modeling. This is actually will be a combination of different models, and we can quickly get the solution with these models. So the time scale and the long scale could be very large. Then I will provide some details for the methods and applications at different scales. So first, we will start with the Benetian modeling. So we know with the Benetian modeling, we can get parameter-free prediction from the quantum mechanics or quantum chemistry. And it will provide widely applicable range of thermodynamic parameters as temperature, pressure, and other thermodynamic properties. These simulations are doable, but usually very expensive. So maybe up to 1,000 items. So usually we will use the density functional theory and the Benetian molecular dynamics simulation to do such simulations. And the application includes like the chemical reaction modeling, because only in Benetian modeling we can simulate the chemical bond breaking or new chemical bond generation. And so because these are in chemistry, these are related to the ion pair separation or generation. And we can also do some electronic magnetic property calculation with this modeling method. Also the explicit solvation modeling of ion in solvent. For the atomic modeling, we will need parameters from the initial modeling or experiment. But when we fit these parameters, the thermodynamic parameter, the range of the thermodynamic parameters would be limited. And this is affordable for more than 100,000 atoms. But in this method, it is a bit difficult to accurately include the chemical reactions and the complex polarization effect. So usually we will use the classical molecular dynamics simulation or atomic Monte Carlo simulation to do such modeling work. The applications include like the thermodynamic properties calculation of fluids, or the dynamic property calculation, and also some like structure property calculation of the interface system. Then we will go to the mesoscale modeling. So the mesoscale modeling, it will need some parameters from macroscale modeling, or we can also get parameters from experiment. This is not expensive for even 0.1 billion items. And but there are only certain or no chemical details are conserved in such mode. So there are a lot of methods at mesoscale, like the coarse-grained molecular dynamics simulation, Brown dynamics, dissipative particle dynamics, phase field, and kinetic Monte Carlo. So the application examples could be the hydrodynamics of electrolyte fluids, or the phase structures and the phase separation of the membrane like the separator in battery. So for the process modeling, it is already in the continuum level, and we will need to calibrate the parameters from experiment in this model. And usually we know these are physical models at the continuum level, so we can describe them with ODE or PDE. And in these models, there's no chemical details. So usually we will use the computational fluid mechanics or the continuum mechanics to solve them. The application includes like the macroscopic structure and the mechanical properties calculation of the electrode, and also some heat and the mass transfer of fluid in a channel. For the engineer modeling, we will need parameters from other models. And usually these are mathematical models at the system level. So there's no chemical details or even no physical details. Because we will need a quick response from this model, so we can get the performance of the system. We will need some reduced order model at this scale. And one example is the battery management in energy storage. So we will need different sub-models from different application, and then combine them with a reduced order model to get the performance of the whole system. So when we know these multi-scale modeling methods, so how to build the strategy for a realistic problem is the next question. So usually we can build the multi-scale model with two different styles. The first one is the sequential multi-scale model. So for the sequential multi-scale model, the models at different scales are connected implicitly. So the high resolution model, for example, at the molecular scale, will be used to generate necessary parameters for the model at a larger scale. For example, so if we want to study the graduation reaction of an organic species, we can calculate the reaction at the molecular scale, and then the reaction rate constant can be transferred to another model at the cell scale. So the biochemical kinetics can be studied on the cell level. So this type of model is dominant in the applications of multi-scale modeling. While we know some information may be lost when passing the parameters from one scale to another scale, which will increase the uncertainty and affect the accuracy of the model prediction at a larger scale. So how to design the key parameters and compensate the loss of information are very important to build a good sequential multi-scale model. Also, we can build the model not only the bottom-up way, but also the top-down. So the parameters, we could get these parameters from a continuum level and pass it to a lower scale. So regarding the concurrent multi-scale model, the quantity from the macro scale and the macro scales are simultaneously computed. So for example, this is like a open system of the biomolecule in solution. So we can simulate the biomolecule with atomic model and also the solvent molecules around it. When the solvent molecule moved a bit far away from the biomolecule, we can change its resolution. And if it, for example, if it's moved very far away from this region, we can use a coarse-grained model or even a continuum model. But when the molecules is very far away from the our target molecule, we will need at least one interface in space to change the resolution adaptively. So in this type of model, actually we can also include different scales model, but we will also need different interfaces. So we know the in the concurrent multiscale model, the solver proceed with the computations of the overall models, and the concurrent model can capture the behavior of the system at different scales simultaneously. But also it will increase the simulation cost in comparison with the sequential multiscale model. So in this work, I will still use the sequential multiscale model. So I just talk about the traditional multiscale modeling method and the how to build the multiscale model. But now we have another tool, the machine learning. So when we have machine learning model, the multiscale modeling construction would be a bit different. So one way is we can build the multiscale modeling model with just using these different simulation method to generate data to build a computational database. And also we can build a experimental database with these parameters. So then we can combine them or just use one of them to build a data-driven machine learning model. And the machine learning model can predict the properties at a certain scale. It depends on the training data at the scale of the training data. Also, when we have some experimental data, it will improve the machine learning model prediction. But there is another way. So when we have when we use the machine learning model, actually we can encode this information or the data from a high resolution or a high scale, and encode this information to a machine learning model, and then we can just pass this model as a whole parameter set to the model at another scale. So this machine learning model, it can include both the data and also the physics, the known and the unknown physics, and encode this information to a model at another scale. Or even we can build like different surrogate models at a different scale to replace the physical model with different machine learning method. So in this way, I will call it the data and the physics-driven approach for the multi-scale modeling. So compared with the traditional method or the pure data-driven method, in this method, we can include more information or more known or unknown physics between scales. So we can expect the prediction of the model would be better than the previous model. So here I will just show you an example for the multi-scale modeling framework with machine learning. So first, we will start with the atomic scale. We will do some atomic simulation to get the data of fluids. Then we will build a neural network model to get the interaction of this fluid at a coarse-grained level. So then we will get the coarse-grained potential with the neural network. And then this neural network will be combined to a DPD or GLE, or general Lagrange equation framework. Then we can reproduce the dynamics of the model. So then I will run some coarse-grained simulations with this model and generate coarse-grained data. This coarse-grained data can be used to train another machine learning model, and the machine learning model can predict the velocity profile at the meso scale. So here I will show how to do it in details. So for machine learning system, for molecular system, so if we consider a d-dimensional system with n atoms in the canonical ensemble, so the configurational distribution function can be defined like this. So Q is the position of the atoms, and the VQ is the interaction potential. So J is the partition function. In our simulation, we selected the octane liquid as an example, and the all atom simulations were performed with the compass force field. So the compass force field have been proved to a good force field to simulate these fluids, and it can reproduce the properties like thermodynamic properties and the dynamic properties accurate. So the coarse-grained variables can be defined as a reduced subset, the reduced set of the atoms. Here I just use K. And then when we define the coarse-grained variables from the atomic variables, we can get the mass of the coarse-grained variables and the momentum of the coarse-grained variables. So so we know the selection of the coarse-grained variables, or I mean the position of the coarse-grained variables is sensitive to the structure property or the structure or the probability distribution function of the structure. And also we know the dynamics is also relevant to the selection of the coarse-grained variables. So that would be interesting to compare them, and because sometimes maybe they are not the same position. But in this system, I just coarse-grained one octane molecules to one coarse-grained bit. So they are the same. And then the configurational distribution of the coarse-grained system in the projection of the configurational distribution of a atomic system can be projected by this one. And then we can get the interaction potential energy and the force on the coarse-grained set. So we can the interaction potential U and the force can be defined like this. So the above are the mathematical distribution of the coarse-graining process. So to do the coarse-graining, generally we will need 3 steps. So the first one is to determine the degree of the coarse-graining and select one or multiple quantity of interest. And the second step is to select a function or several functions to represent the interaction potential between the cross-grain set. And the third one is to optimize the parameters in the functions if these functions are analytical. So to reduce the difference between the values of the quantity of interest between the cross-grain simulations and the reference simulation results. But this is for the traditional construction of the cross-grain model. But now we know but now we have another tool, machine learning. And if you compare these steps with a machine learning model training, you will find they are very similar. So following the same step, we can build or we can get the interaction potential function U with a neural network. And so here this U hat is equal to U cosine theta, and the theta represents the neural network potential, the neural network parameters. So we will need the input for the neural network. So generally, we can use the position of the atoms as the input, but the model training would be not easy for this input descriptor. So we need to convert it.
Peiyuan, I have a question. How many atoms do you consider for this octane molecule?
We have 2,000 atoms, 2,000 molecules there. Yeah.
And it's a 3D, right?
Yes, 3D model. Yeah.
Yeah. Thank you.
Yeah. So we will build. So first we will need to find some descriptors to describe the environment around the one molecules. So here I just used some local descriptors. So the local coordinates of the cross-grained site is constructed by the position of the cross-grained site and its first and neighbor nearest neighbors. So we can define the vectors from the cross-grained set I to cross-grained set G. And then we can calculate the local descriptor matrix. And here I also used a smooth weighting functions as here to decay the function to 0 at a card. Then we'll need a local embedding network maps from a single value SR to N1 outputs. So actually, the metric form of G here is the local embedding matrix GI, which is belong to R N1 times N1. And also when we do the cross-graining, we will also need to keep the translational invariance, rotational invariance, and the permutational symmetry. So here, the encoded feature matrix Di of cross-grained set I can be defined like this. And the symmetric matrix R tight times R times T is the overcompleted array of invariance with respect to the translational and the rotational invariance. So we can make sure they are satisfied with these conditions. And the subnetworks associated with the same type of particles share the same parameters. So it will also keep the permutational symmetry. This is what I did currently, but I'm thinking about this encoder matrix may be replaced by the equivariant neural network. So this is an ongoing work.
Hey, you and I have a question again. So here you're considering a standard FNN, right? But the equivariant neural network is a graph neural network.
So
you're not doing a graph neural network, right? You're
not
doing
a graph network. Yeah.
But the equivariant neural network is a graph neural network.
Yeah. Yes. I know that. Yeah.
So basically, you're saying you're going to move from the FNN, fully connected neural network, to a graph neural network.
Yeah, that would be
equivariance. Yeah.
Yes. But we know that for the equivalent neural network, naturally it can keep this invariance and symmetry. So I'm just think about it.
Okay. Sure.
Yeah. So in our model, the output, the target property is the false. This is also a very straightforward property. And here the C is the configuration, the number of configurations in the training data. There are some other methods like the statistical trajectory matching method. So in this method, they include the conservative, the conservative and the non-conservative false simultaneously, and consider the entire time evolution process in the training. But if we combine them together, so that means we will need to reproduce both the structure and the dynamics with one in one step.
Can you explain what is FIR? Are these so the gradient of the potential? That's the conservative force that you'll get right after. What is the first part?
You mean this one?
Yeah.
Oh, this is just our
Oh, it's what you want to do because you try to minimize this. Okay.
Yes.
But this is just from the definition, basically, of the force.
Yeah.
Okay. So L is your loss function.
Yes, that's right.
Okay, sure.
Yeah, and here I show the results. So this is the total energy and the absolute value of the net force on the atom. These are our this is our training properties. So we can see we can we can reproduce these properties very well. And also I calculated the GFR with the trained machine learning potential.
You didn't tell us what. Sorry, but you didn't tell us what's the coarse graining degree. How many?
Oh, that's the one molecules to one coarse grain bit.
Oh, so there's no coarse graining then?
No, we have coarse graining. So in octane molecules, there are the chemical formula is C8H18. So there are 26 atoms in one molecule.
Oh, I see. So 26 atoms to one.
To one coarse grain bit, yes.
Okay, that's the answer. 26 to 1. Okay, I got it. Yeah.
Yeah. And but when I coarse grain it into one bit, so there's only non-bounded interaction between them. Yeah, and then I calculated the GFR here. The GFR here is you can see this is not a one peak distribution. So for such GFR with such shape, it is difficult to reproduce with the analytical function, but now we can do it better with the neural network. Then I will try to add dynamics to the system to improve the dynamics. Because when we do the coarse graining, although we can reproduce the energy and the force, but because we changed the resolution of the system, actually we will lose some, for example, like entropy in the system. So the dynamics at the coarse graining cannot be the same as the atomic level. So first I try to include the DPD into the with integrated the TPD with the neural network. I also tried both TPD method. One is the convolutional TPD method, and the other is the transverse TPD. So from these results, we can see we can reproduce the long-time dynamics of symploid with the neural network, and with either the conventional TPD or the transverse TPD. But for the conventional TPD, we will need a much larger fraction coefficient here. So determining the appropriate complexity of the configuration of the velocity-dependent friction force, this is required for some specific case. For example, like this is the example for the star polymer, and if we are interested in the short-term dynamics, so we can see different scaling at different time range. So in this case, we will need so if we are interested in the dynamics in this part, we will need a time-dependent memory. And also, even for some simple molecules, for example, like this bromine substitute benzene molecule, we will also need, we can also see if we define the distance between this bromine, the red sphere, and the carbon atoms on the benzene ring, we will find two stable states for this molecule in solution. So we can see there are two peaks if we calculate the PDF of the. So for such molecules, we will need a state-dependent memory. This is ongoing work. This is also a collaboration with Huan Lei in Michigan State University. So for the state-dependent memory, for example, for a Hamiltonian system following the Zwanzig projection formalism, so we can get the Q dot and the P dot here, and here the kernel is like this. So we can do a summation for the kernel like this. So here the L is the Liouville operational corresponding to the auxiliary dynamics. The C are the channels represented to the coupling, the result, and the auxiliary variables. So the C can be represented by a set of state-dependent features like phi q. Q is the position of the particles, and phi so phi here encoded the nonlinear coupling between the resolved and unresolved variables, and the sigma t represent the dissipation between feature phi qt and phi q tau. So here the operator will induce non-Markovian interaction among the features with the time lag of tau characterized by the kernel function. So as a special case, at the Markovian limit, sigma t is proportional to sigma t. This equation covers the Landau dynamics under the quadratic form of phi t times phi ensures the positive energy dissipation. Also, by choosing sigma t to be diagonal with individual components corresponding to the certain frequency models, the equation reduced to the heat bus model, and with a nonlinear coupling of bus coordinates. So on the other hand, the present model enables an adaptive choice of the number of spatial features and a more general form of phi-t with the off-diagonal components capturing the non-Markel coupling amount features. So this is critical for reproducing the collective dynamics. And then so we can rebuild this reduced dynamics like this. So then we need to solve the phi qt and the sigma t. For the details, I will recommend to our archive paper. This is almost done, but I'm still working on how to integrate this state-dependent method to my framework. So then, after we build the mesoscale model,
Peiyuan, here the fluctuation dissipation is automatically satisfied, right? Because you chose the kernel like that.
Yes, yeah.
Okay.
Then I built I used the Cosgreen model to perform the postulator flow with some complex boundaries. First, I ran the Cosgreen simulations to get the data, to get the velocity data at a different position for a complex boundary. So here the boundary, I just used the sine function to simulate it. And then I trained a neural network model with the data to predict the velocity profiles at a different position. So here I show the results at, for example, at the peak of the same function or the middle part and also the valley for different boundaries. So here we can see the prediction on the peak is pretty good. And for the valley, it is a little worse, but it is still acceptable. So that means I think that's because at the valley part there's a few data in the Cosgreen simulation. Also I started the small dynamic of fluids with the physically informed neural network. So first, I will just give a brief introduction for the integral equation theory in the thermodynamics of fluids. So generally speaking, the integral equation theory simplified the explicit overall description of the solvent into a density-based distribution around the solute. So by considering the molecular structure and the correlation effects, so the IET can provide a realistic distribution of the solvent molecules surrounding the solute, so which approaches the explicit solvent molecular dynamic simulation in accuracy. And besides the density distribution estimation, so the IET can also calculate other properties like the solvation free energy of the molecule in the system. So the most developed IET for the solute solvent system is the 3D reference interaction set model, like I showed here. Actually, this is similar to the classical density functional theory. And in this theory, the Austin-Serknak equation is the key equation. So let's start with a simple case. So in a isotropic fluid with density rho and a pair distribution functional pair function G of R, so the Austin-Serknak equation defines the direct correlation function HR in terms of the total correlation function, like this. And the OZ equation establishes the relationship between the total relation function HR and the direct correlation function CR, like this. So because the functions HR and the CR are both unknown, so we will need an additional equation, which also we also known as closure relation. So like this. So here the gamma R is the we call it the indirect correlation function. Gamma R is equal to HR minus CR, and the BR is the bridge function. Defined for specific applications, and it can be expressed as a power of series in row of irreducible diagrams. So UR represents the interaction potential between particles for a specific fluid. And people have developed different various closures, like the agency closure, PY closure, OM closure. They have different analytical function forms. And you can see some of them is very complicated. On the other hand, if we fix the form of B of R, and if we turn the U of R, so because the parallel correlation function G of R can be determined in experiment, and then we can solve this equation inversely and learn the interaction function UR. It can be used as a Cassegrain interaction potential with a top-down Cassegrain method. So first, we try to solve the OZ equation of a simple fluids with physically informed machine learning. So in this case, we use the agency closure, and the unknown of the OZ equation, the gamma R. We know it is characterized by a sharp gradient when R is close to 0. So to improve the training of the neural network here, we have some trick. So we define a capital gamma R is equal to R times gamma R. And so we will change the function, the shape of function like this. And also we do the same thing with the CR. And the neural network was trained with an initial function like an exponential function with CS to 10 and BS 3. So for the gamma R, we have known it will oscillate around 0 with waves whose spectrum cover a wide range. And for the physically informed neural network training, it can suffer from a spectral bias problem. So that means it tends to learn the low frequency model. So to address it, we do a straightforward transformation of the normal coordinates gamma tet into multiple Fourier features. And the transformation is constructed by a random Fourier mapping. Here we define SF. So SF is equal to this one. And the BR here is a random vector, and the M is the number of Fourier features. The elements of B were sampled from a Gaussian distribution. So here, this is our workflow. The input is the R, and we converted the R with the Fourier transform to convert it to the Fourier features SF. And here we use this is input for modified FNN. So for the modified FNN, I recommend this paper. This is Paris' work. And then the output for this FNN is the gamma R. So then we can convert gamma R to CR and the CR to C caret Q, and then get the gamma caret Q, but then get the gamma star R. So finally, we can build the loss function is like this, and so we know the boundary condition, the gamma 0 is equal to gamma max is equal to 0. And this is the results for the OZ equation with the agency closure. So here we can see we tested it with different densities. When the density is low, for example, 0.1 and 0.5, we can see both of them are agree with the simulation very well. And when the density is higher, for a pin without the Fourier features, it cannot capture the oscillation at the for the long correlation part. But if we include the Fourier features, the pin model can accurately capture this oscillation. And then we also tried the inverse problem. So the scattering experiment, like the light scattering or the small angle neutron scattering, this is we can get the structure of the solution from experiment. So the data from experiment is just a curve. This is the relationship between Q and IQ. So this is in the reciprocal space. We know IQ is equal to PQ times SQ, and the PQ is the form factor, which describe the size and the shape of the molecule, and the SQ is the structure factor, which describe the interaction between the molecules. So we know the relationship between SQ and the G of R is we can just do a Fourier transformation to get each other. So here we use the pin to infer G of R from experimental data of the liquid argon. So the workflow is like this. We start with R and get SF. Then we this were inputted to the FNN, and then we calculate G of R. G of R was transferred to SQ. Then we build those. So this is the results. So here we can see our result. Our model can perfectly reproduce the SQ in the range of Q. But for G of R here, we can see if R is beyond about 3, we can get a perfect match. But at the beginning, we can see some fluctuation. So, but in physics, the fluctuation behavior can be neglected because the exact G of R in the small R region, it should be there. Then we compare the prediction between various of closures. So we tried PY, HNC, and VM. The pin solution are stable for each closures, and the prediction at the rho is equal to 0.1. They're almost the same. So this is consistent with previous simulation. And we can see the difference when rho is greater than 0.6. So and for the VM closure, it showed the largest oscillation amplitude. Then we also try to change the U of R. That means we test the different type of fluids. So we fix the closure. Here we use the VM closure. and test different fluids like the hard sphere fluid, square wells fluid, and Lennard-Jones fluid. So we know for the hard sphere and the square wells fluid, the potential functions they are not continuous. But in our results, we can see our PIN model can capture this discontinuity for the hard sphere and the square well fluids. And we see the short range correlation increased with density for all the fluids, which also increased the local density difference. So obviously this the local fluctuation in the short range is not so strong for the potential function with a small attractive part like the Lennard-Jones fluids. And also we can expect we will need more residual points if the local density difference is larger. We also calculated the compressibility factor using the virial equation of state. So especially because it has a strong connection to the discontinuous potential functions inherent to the hard sphere and the square well fluids. So we found the contribution to the total error from the discontinuity points is greater than from the middle points. The thermodynamic property like Z is mostly relevant to the value of GFR that are close to the discontinuity points. And the prediction error of Z of the hard sphere and the square well fluids narrows within small density. For example, like 0.1. So you can see the relative error is very small. But the density is 0.7. The relative error of the square well fluids is still small, but increased a bit. And we so if we want to simulate an even higher density fluid system with strong local fluctuation, so yeah, we can also expect we will need more residual points to reduce the error. So finally, we also want to predict the fluid structure at various of thermodynamic conditions with the OZ equation. So we developed a physically informed dipole net model for the solution of this is like the parameterized OZ equation in mathematics. So the loss function here is like this. So we also have the boundary condition for gamma, and we use the R as rho and the rho as the two inputs for this dipole net model. The Fourier features embedding is only applied to the trunk net. Also, we know we can use other thermodynamic properties like temperature. Yeah, they can also be used as the parameters. So the trunk net takes R as the input, and the branch net takes density as the input. So here are the results for I used a 12.6 Lennard-Jones fluids with the VM closure as the example. So here we can see from the contour plot of gamma, the maximum oscillation amplitude and the oscillation frequency increased with density. Also, the oscillation decays slower to 0 with increase in R, and the maximum absolute error for the PIN dipole net model is near the corner. But here the absolute value of gamma is also, we know it is also large here. So yeah, that's what we can expect. Yeah, and yeah, this is the last slides that I have. So thanks you for attending, and please feel free to ask questions.
Thank you so much, Dr. Peiyuan. It was a really nice talk. Do we have any questions from the audience?
Oh, hello, Peiyuan. I'm Guansheng Li, a postdoc at Crunch Group. I have two
Hi, Guansheng.
questions. First is, I also use DPD to simulate the red blood cell. Do you think is it possible to apply this method to compute the red blood cell? The main difference of the red blood cell is blood cell has structure. It can deform compared to the particle.
Yeah. So I think so if the deformation is strong, yeah, you will also need a state-dependent kernel. Yeah.
Okay. And the second question is, did you try to I remember you have predicted the computing the posture flow in the curved structure.
Yeah.
Did you try to compute the fluids in different geometry, like open boundary? I think right now is a periodic boundary condition. Yes.
Yes, you're right. Yeah.
Did you consider the open boundary?
I have not tried the open boundary.
Like bifurcation.
Yeah, I know that. Yeah. But I think this is a good question. Yeah. Maybe I can try it in the future.
Yeah, because in the DPD simulation, it's not very easy to apply the open boundary condition.
Yes.
I think if this method can apply to the open boundary condition, it will help us to.
Yeah, I know. I know Chen Li has done some works, but not using neural network.
Yeah.
Yeah.
And because in DPD we have three types of force. Did you also predict the force compared with the output from DPD, or you just predict the coordinate of the particle?
No, I didn't, because so if you want to predict the three types of force simultaneously in one model, we will need something like they call it the trajectory mapping method. So in that case, we can include both the conservative force and the non-conservative force at the same time.
Okay, thank you. It's a very nice work.
Yeah, thank you.
Okay, Peiyuan, I have a question. I think it was not clear the point where you were trying to compute the memory kernel and also state dependent, but let's say memory kernel.
Okay.
That's a very difficult problem.
Yeah.
And as you know, the memory depends on the degree of coarse graining.
Yes.
If the degree of coarse graining is 0, the memory is the delta kernel, the delta function.
Yeah.
Can you didn't show any results. You said just go to the paper, but no time to go to the paper. Yeah. Can you tell us what is given? So because it's not even a well-posed problem to find what do you know so that you can compute, even with this approximation that you're doing here, to even if you parameterize, you have to assume, I see the positivity that you have with the fees and stuff, but can you set up the problem for me? What is that you assume in order to find an approximate memory kernel, which somehow should incorporate the effect of coarse graining? Because if I don't do any coarse graining, I should go back to 1. I do very little of the delta function, basically.
Yeah.
How do you do that?
Yeah, so actually our target system is this molecule. Yeah, this molecule in water. And there's only one molecule in water.
Well, I don't know. Let's say let's do the star polymer that I know. You course grading the star polymer, right? Let's say
Yeah.
11 to 1 or something, you know, whatever. The one in the middle and 10 molecules, 10 atoms, so you got one particle. So above 10, above that, you have a memory effects. How do you
Yes.
compute that kernel? Generically, not for one case so that you don't tricks. How do I compute the kernel, a memory kernel that is required for coarse graining? I didn't get, I don't think you explained that.
Yeah, and I also, yeah, as I also mentioned, so the degree of coarse graining also affected the conductive force and also the dynamic force.
I know that. I know that.
Yeah.
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 How do you compute the kernel? What do you know? First of all, what is the data? What do you know? You know, you have realizations of from the atomistic simulations, right?
Yes, yes.
You have a lot of simulations. How many? Thousands? 1,000? How many? Because you need a lot to build a function. We tried to do that, and it was, even with the graph neural networks, we couldn't succeed. Panos was part of it. He knows that we never finished that work.
Yeah, I agree with you. So,
no, but you
so,
said that that you published a paper where you have it.
No, this is still ongoing work. Actually, yeah, because I said this is a collaboration work with Huan Lei in Michigan State University. Yeah,
I know him. He was my student. But what's the idea? Just tell us what's the key idea. How are you gonna get the kernel?
So this is so in my current model, actually, for simple fluids, we don't care about the time dependent memory because this is very
fine, stationary. Let's say stationary kernel. That's fine.
Yeah. But if this is for example for the star polymer, I agree. Yeah, for something like this in this part, this would be quite difficult.
Okay.
Yeah.
Thank you. Do we have any other questions from the audience?
Are these codes available? Are they on GitHub or these are your personal codes that you have developed?
This is my private code. Actually, yeah, for this part, most of the code are from Huan Lei.
Great. It looks like we do not have any other questions, so I think it's time to close this session. Peiyuan, thank you so much for your time today. It was a wonderful talk. Thank you everyone for your time today. We had a single speaker today, so until next week.
Yeah.
Thank you.
Thank you, Peiyuan.
Thank you.